this computer, then we'll share this whiteboard, and we'll keep going with it. Okay. So last time we were talking about not magical. In fact, we argued it's really not magical. It is a new constant in math that you may or may not have seen before. We just call it I because that's exactly what it is. And so with I, it is the square root of -1 that defies kind of our normal understanding of things, but that's also just how it works. That's just the way it works. Um, we can't really get into the deeper kind of conceptual purposes behind it simply because it does go a bit beyond the scope of what we study. But what we find out is that I is necessary to solve certain types of equations. There's literally no possible solutions to certain equations without I. So I is very important. So, a few things we went over last time. We talked about adding and subtracting complex numbers. We talked about the definition of a complex number. And that was fine and dandy. There's a few other things we can do with all this. Let's say in general, you did take the square root of a negative number. Say you had the square root of -4. Well, there's a cool way that you can basically deal with that. There's a cool way that you can simplify that. What we can do, we can actually branch off a -1 because -4 is really the same as 4 times -1. So inside that square root, we do 4 times -1. I'll put it in parentheses just to be safe. Furthermore, we can go another step with that, and what we can say is that, oh, well, wait a minute, -1 and the 4, whenever you're taking the square root and you're multiplying in the square root, you can branch those off into 2 separate square roots that are then being multiplied. Okay, that's cool. That's cool. Why would we ever want to do that? Are we just playing around with the math for no reason? No, not at all. Because check this out. Square root of 4. What does square root of 4 become? Or rather, what is the square root of 4? Well, let's think. The square root of 4, what's a number that multiplies to itself and gives you 4?
He said 2. You can't hear him.
Oh, okay. Sorry. 2, exactly. And then what is the square root of -1?
Put together. 1, 2, 3. Yeah, say it. Say it loud.
You what? No, I'm kidding. I know. Little math humor for you in the morning. Yes, 2i is what it's going to ultimately become. So we took square root of -4, we turned it into 2i, and that's a little bit easier just to look at. It's a little nicer on the eye, no pun intended, visually speaking. So that is actually something we're going to do. In fact, we're just going to say we can warp to it. If you had, say, square root of -85, well, here's the rub. 85 itself doesn't have a nice clean square root. So ultimately, what we're really just thinking about doing is taking an I out of that in order to get rid of the negative sign on the inside of the square root. And now it's gone. It's gone, baby, gone. The square root of 85 portion, though, it really just does not simplify at all. It's just square root of 85i, and that's your final answer. Just keep in mind the I is on the outside of the square root. It's been cast out. So give me 1 second. I'm going to jump in with my iPad so I can see what you guys are seeing, and I just need to get the Zoom ID to be able to do that. Bear with me for 1 moment. 9143. All right, so now I'm jumping in with y'all. I'm going to mute myself. Mute myself. Okay, back to it then. Okay, so this is a really convenient tool, and I'm serious. We're going to warp to it. We're just say, oh, you got a negative on this inside of the square root, bring it out as an I, and if you can simplify the square root portion, do it. But most of the time, you're not going to be able to. So last time we said, okay, what can we do? Well, we can add complex numbers, we can subtract complex numbers, we can multiply complex numbers. That's great and dandy like apple candy, but here's the thing, dividing by complex numbers and things get a little bit nasty. You don't divide the usual way you would think to divide. But before we can talk about how to divide, we have to introduce the tool we're going to use, and that's called a conjugate. A conjugate. A conjugate, a conjugate. What a conjugate is going to do is it's going to give us a little trick for getting rid of I, but it doesn't always work. And you'll see what I mean in just a moment. So you remember last time we said that the usual form of a complex number is a plus bi, where a and b are just some real numbers, so it could be 3 plus 2i, and then I is the constant. It's going to have something called its conjugate. Every complex number has a conjugate. You simply flip the sign that's in front of the I portion. So the conjugate of a plus bi is a minus b times I. So this thing's conjugate is that, but vice versa is also true. This thing's conjugate is that. And so for the time being, we're calling that conjugate, we're just thinking of it as a little special, like the twin. It's on the other side of the coin of it. Now you're probably thinking, okay, all you do is flip the sign in the middle. Why in the world would we ever care to do that? Well, let me show you something cool, folks. Whenever you have a complex number and you multiply it by its own conjugate. So let's keep it simple. Let's say you had 6 minus 4i. Let's say that's the complex number you've been dealt in the great game of math poker. And you want to multiply it by its complex conjugate. There's going to be a reason to do that. Well, the conjugate of 6 minus 4i, bada bing, just flip that sign in the middle. It's always got to be the sign associated with the I portion. And now, as we talked about last time, we're going to need to FOIL that bad boy. We're going to need to FOIL it. And I'm about to go full John Madden here. If you know who that is, cool. If not, that's okay. And I'm just going to write on everything. Let's see, I got to do the 6 times 6. I got to do the 6 times the 4i, and it's positive. And look what magic is going to happen here. Then I do negative 4i times 6. That's going to become minus 24i. Ooh, and wait a minute. When I combine like terms in just a moment, that's going to go away. Finally, I do the negative 4i times positive 4i. Negative 4 times 4 is 16. And then I'm doing I times I, which is I squared. So that's what that becomes, but like I mentioned a second ago, this is gone. You combine like terms, you add something, then you subtract it off, get out of here, it's gone. That 36 didn't go anywhere. But then remember, I is the square root of negative 1, so what is I squared? And you can just type it out in the text box if someone knows. But we might remember that I squared is negative 1 itself. So, and I'll have the, very good. Thank you, Raina. You are absolutely right. So, not a text box. Minus 16 times negative 1. So I was trying to put a text box on here. You're bad. I do not want to work with me right now. Draw. There we go. So I'm sorry, so 36, and then it's minus 16i squared. That's just what we started with, but since I is negative 1, that really becomes 36 plus 16. And a little bit of mental math will tell us, 36 plus 20 is 56, go back 4, so you're down to 52. So I'm running out of a little bit of space there. But ultimately, that's going to become action 52. There we go. Very nice. So let's see the forest for the trees. The whole reason, the entire reason, 100%, that the conjugate just has a flipped sign is because it creates this scenario in the middle that when you combine the like terms, the I portion goes away completely. You still have the I squared portion, but that's going to become a negative 1. And all of a sudden, you've completely rid yourself of the I. So the complex conjugate, that's all it is. You're flipping the sign in the middle to get this wonderful effect going on right here. So by multiplying a complex number by its conjugate, we get away from I, we get just a strict, pure, real number. So now, why do we care about that? Why is that important? Why is that special to us? Well, let's say you did need to divide complex numbers. Let's say we're ready to do with it, we're ready to throw on the gauntlet or throw down the gauntlet, whatever the saying is. Let's say you had the number 4 over, or 4 divided by 3 minus 12i. Let's say that's what you're dealing with. That's the problem du jour. Well, normally I would just say, well, it is what it is. I'm going to leave it like that. But we can't just do that here. We're going to try to find a way to actually perform the division and simplify things. So our traditional method of doing it is not going to work. It's not like I go write out 3 minus 12i and then I put the division thing and then a 4 and then I try to long divide it into a 4, because that just doesn't really make intuitive sense. Although, believe it or not, there's a way to do it that way. We're not going to bother. Here's what we're going to do. We're going to appeal to that conjugate. We just said the conjugate is something we can multiply a complex number by to get rid of I, to get I just completely out of the picture. So if I could, me as in me, if I could get rid of the complex number in the denominator, boy, life would just be great. Well, in order to do that, I'd have to multiply it by its own conjugate, as per what we just discussed. But wait a minute, I'm just coming in here and saying, okay, just multiply only the denominator by this thing. Am I allowed to multiply just the denominator of a fraction by some number? Well, generally, no. I'm not going to end up with the same number. I'm going to end up with something different. So if I do it to the bottom, I'm going to have to just be fair and multiply by that same conjugate, and that's a 12, on top. And yeah, that's exactly what I'm going to have to do. And so we follow our mathematical procedure here for dealing with this. What I would argue is think of it as like the denominator's also in parentheses, because what you're saying is multiply the whole denominator here, multiply this whole denominator by this whole denominator, the whole thing, which means you're going to have to FOIL. Up here, you're going to have to distribute. You're going to have to take this 4, distribute it over here in order to simplify. And let me press. So let's do it. Let's jump in. On top, you're going to get 4 times 3 is 12 plus 4 times 12 I, which is going to become just 48i. Make sure everyone's muted if they need to be. There we go. So that's what that will become on top. On bottom, though, you're going to have to come down here and just as a little side, and we're going to have to FOIL that. So let's see, we're going to get 3 times 3 is 9, plus 36i, minus 36i, minus 144, 12 times 12, I squared. And using that little trick earlier, this is gone, baby, gone. That negative 144 I squared is actually going to become plus 144 because the I squared basically will flip the sign on us. Now I know what you're thinking. You're looking at this thing here at the end and you're saying, Josh, that's not really a whole lot better. And yeah, I agree. It's still not exactly a whole lot of fun, but it just, to us, dividing by I just doesn't sound right. But dividing by a real number is a little bit easier to deal with. There's also one more thing we can do with that. We can split up the numerator. And you'll see what I mean here. Over 153i. And so what you see, we split up the numerator because remember, if we wanted, this would all combine back into the same fraction. You put the I on it. But by writing it like this here at the end, that conforms to the standard form of a complex number, where A is the 12 over 153. B is 48 over 153. And then you just have the I standing kind of next to it. So that's how we perform division. This thing is actually equivalent to this thing down here in the bottom right. So I don't want to just keep going nonstop. Using the text box in Zoom, do you guys have any questions for me? Any questions over what we just did there? Questions, comments, concerns? If not, we are ready to rock and roll. And I'll double check here. Let me open my next set of notes. So that, in a nutshell, that was section 1.3. That was section 1.3. And we are ready to move on to section 1.4. And yeah, absolutely feel free to use the text box in Zoom. It should like jump up and down at me and say, hey, you got a message, so I'll know to stop. And let me know if there's anything you need help with, something's not making sense. I know it's a little awkward using Zoom. We'll just call it like it is, but we will do our best. So we're ready to move on to section 1.4. And if you've never seen it before, that is the section sign, or kind of like a subsection. It draws from philosophy. Really, the proper way to draw it is like this. And you imagine it's all connected there, like there's a circle in the middle and 2 hooks over it. It's pretty cool. You should start using it in your own personal life. Enough said about that. What we're going to do is we're going to be dealing with quadratic equations. Quadratic equations. And quadratic equations are great. They're super important. Really, we're going to see almost right away, as we attempt to solve quadratic equations, a reason to use I in the first place. Because it turns out there's going to be some solutions to quadratics that simply involve I. Then there's no way around it. You can't dance away from it. So let's introduce the standard form of a quadratic equation. So this is called the standard form of a quadratic equation. And it's going to look a little something like this. Boy, they love using A, B, and C. So I'm going to use A, B, and C here. We used a and b earlier to define a complex number, but it's not the same a and b. It's just saying it could be any number. So the standard form of a quadratic equation is a x squared plus bx plus c, and you could say it's equal to 0 if you want. Now, I'm sure most of you have seen a quadratic before. The a, the b, the c, we call them the coefficients. The coefficients. And then you just put it in alphabetical order. So A goes with the highest powered term, B goes with the next powered term, C goes down all the way. Because you can also have a fifth degree thing where it would be ax to the fifth plus bx to the fourth plus cx to the third, etc. So that's all they're doing. One thing that we should really note is that A shouldn't be 0. A should not be the number 0. Because if it was 0, what are you really doing? If it was 0, what you're saying is that this term really just goes away completely, x squared and everything.
Good morning. Please excuse this interruption. It is picture day, so we need junior students with the last name starting A through D. Please report to the cafeteria.
I would say you can go later. Yeah, I wouldn't. Don't go now. No. I'll take care of it.
Cool. So, okay, so yeah. So basically, if A was 0, this would all be gone. So no, don't make A 0. Otherwise, you're not dealing with a quadratic. The spirit of what makes it a quadratic is this guy, the x squared part. And it has to be the highest power term. If your highest power term was x to the third or x to the fourth, you're not dealing with a quadratic. But if your highest power term is x squared and everything else behaves normally, you don't have any weird funky powers like on here, that's what makes it a quadratic. That's kind of the spirit of it. Now, what we like to do next is we like to talk about how we can solve quadratics. That's kind of a big deal, finding solutions. And so what we usually use is we use factoring. You can use the completing the square method, and completing the square method is vitally important in mathematics. But depending on what you have, you might also have a simpler method to go with. So let's start with the simple method, but only works in a very specific case. And we're going to call it the square root method. Basically what happens is, let's say you had an equation like this. (3x squared minus 27 equals 0. Now you might remember earlier, let's see if I can undo all the way back to that previous screen, just for fun. Going back in time. Yeah, it worked. You remember earlier, there's 3 terms to a quadratic. So for what we have, this middle term is missing. That's okay. The middle term's not important in the grand scheme of things. It's still a quadratic because this term is there. So the middle term gone. That just means that b, the coefficient of the x term, is 0. And so we just don't deal with that. But back to where we were, if you're missing that middle term, if you're missing b, or b is equal to 0, and there's no standalone x term, then this thing actually becomes pretty straightforward to solve. Normally with a quadratic, you want everything on the same side of the equation. But in this very narrow sense, we would just actually isolate the x squared term. We want to get x squared by itself exactly like you're solving an equation the old school way. Then we need to divide both sides by 3. And you're going to get, I'll write it over here to give it a little pomp and circumstance, x squared equals 9. All right, math cadets, here's where we've got to solve it, because we wanted to get the x squared by itself so that we can then do this. Really, we need to figure out what value of x is going to work here. What value of x can be substituted in here that's going to come out to 9? In other words, what is a number that when squared is equal to 9? Not really a trick question either. What do we got in the text box? We've got, come on, open up. That's what I have it on my iPad for. 3, exactly right. 3 works, but is there another number that works? And -3, very good. You're absolutely right. Think about it, 3 squared is 9, but -3 squared, -3 times itself, the negatives go away and you get 9 as well. You've probably seen that before. We're going to call that the square root property. Whenever you are trying to deal with an equation like this, x squared equals some number, you have to recognize that there's 2 different ways that can go, both the positive form and the negative form. So to deal with that, there's a couple ways to write that. You can say x equals -3, 3. In other words, both -3 as well as 3 work. Another way, a more succinct way of writing it, and this is going to be the overall answer here, is going to be x equals plus or minus 3. And it's exactly what it sounds like. It just, you'll have to recognize from it that this means it can be both +3 as well as -3. Either one works. We're going to actually refer to this idea that solving a simple quadratic like this can have 2 possible answers. We're going to refer to it as the square root property. It gets its own special name because it's important. The square root property. So normally when you just take the square root of a number, you really only talk about, and I'll do it here, you really only talk about the positive square root. So say you were taking the square root of 64. Normally you would just say 8, and you would be correct. That is the correct answer. But just a second ago, we kind of, in a way, we inadvertently took the square root. Josh, how come we did both negative and positive form of it? And it's actually just a really confusing matter of the symbols we choose to use. When we use this symbol, this square root symbol, it's called the principal square root. And it's literally saying, look, we know there's 2 square roots secretly, but when we use this symbol, we just want the positive square root. That's kind of what we're saying when we use that symbol. But if we had to solve the equation, x squared equals 64, you're tempted to just take the square root of both sides. And you're right to do that, but you have to manually remember that when you're dealing with it in equation form, you're recognizing the 2 possibilities. So you need the plus or minus, and then that becomes plus or minus 8. So it's a little bit confusing because whenever you see the square root symbol, it doesn't want you to include the -8. You have to know yourself when you're solving an equation to deal with it that way. So that square root property is very, very important. In fact, it turns out the fact that you have a quadratic and there's 2 different possible solutions to it is massive. It is so fundamentally important to the very structure of algebra. It completely informs algebra for the rest of the semester. So whenever we solve some quadratics, you need to be thinking there's possibly going to be 2 different solutions to them. Not always, though. We're going to see the exception. In fact, what's really interesting is that let's say you had an equation, and I'll clear the whiteboard here. Let's say you had an equation like 3x to the 5th minus 4x to the 4th, blah, blah, blah. No x squared term in there. Let's say you had something nasty like this.
All juniors, last name starting C through D. Report to the cafeteria.
So if you have an equation like this, it will be dealing with some kind of like this later on in the semester. Look at that highest power. That highest power is a 5. And it's also convenient because I wrote it in what we call descending form, where you start with the highest power, go to the next highest power, and so forth. That highest power is 5. That means that if I were to try and solve this, basically set it equal to 0, And I wanted to know what are all the x values that can be substituted into x there and create a true statement, which is all a solution is. There's 5 possibilities. Or rather I should say there's up to 5. That's actually really interesting. So that's why there's 2 solutions to a quadratic. It's because the highest power is 2. But there are exceptions. There are special cases where it turns out there could be 1 solution, but you should always think there might be 2 solutions to a quadratic. And we'll get into more detail with that as we actually get into those. I'm just getting so excited, and when I get excited, I just kind of get carried away a little bit. All right, and there's nothing I can do about that now. We'll try. All right. So with the square root property, we could solve even an equation that looks as nasty as this. Excuse me, not square root. We could solve something like this, because it turns out that square root property, as long as one side of your equation is entirely being squared, which it is here, the whole left side's being squared, and you just have a constant on the right-hand side, the square root property is going to apply. I would take the square root of both sides, bashwa, but I have to remember myself to put a plus or minus with the right-hand side. I just do. The square root and the squared cancel each other out, which is the whole reason we took the square root. I can even drop the parentheses here. I have to manually remember that it's plus or minus 12, and it's the square root of 12. What's even cooler is, well, I haven't completely solved for x yet. I need to get that 4 out of here, so I'm going to add it to both sides. And I can actually do that and make it look like this. 4 plus or minus the square root of 12. And so, wait a minute, now that gives us one more thought. That means the solutions to this, we got to do plus or minus, and we're throwing 4 into the mix. Yeah, the solutions are 4 plus the square root of 12. Also 4 minus the square root of 12. Either one of those is a perfectly valid solution to that original equation, x minus 4 squared equals 12. So I'll pause for a moment and field any questions you guys have. I like this idea of pausing, just to give you guys a moment. Is everything making sense so far? Am I moving too fast, too slow? We're good, we're good? Awesome. And you can let me know if we're not, and if I need to re-explain something. That's what I'm here for. Okay, so what we just did there, that actually gives us a justification for using something called completing the square. We'll deal with completing the square in a moment, but basically we just did complete a square, if you will. And it turns out that this method of completing the square is actually so darn important.
Junior students, last name E through G, to report to the cafeteria.
Completing the square is so fundamentally important to understand what's going on intuitively. So we're going to deal with completing the square at some point a little bit later on in the semester. The next method we're going to learn for solving a quadratic, well, what if that term in the middle, what if that x doesn't go away like it did earlier? That's okay. We're going to try out a method called factoring. Now, I'm just going to tell you right now, factoring, as cute as it is and as much as it is stressed in math curricula, factoring is actually not horribly practical, believe it or not, because things have to fall in place very, very perfectly for you before you even come into the equation. The equation almost has to be engineered with you factoring it in mind, which is kind of not great, because you could just in the wild be given an equation that is just based on something you're dealing with, computer work, engineering, economics, and it's not going to come out with cutesy little numbers so that you can factor it perfectly. So we'll talk about factoring, but factoring is only useful in a very narrow scope. So just keep that in mind. It's completing the square and using ultimately the quadratic formula, which is derived from completing the square. That's where the money is. But okay, let's talk about factoring. Before we can really get into factoring, we got to talk about the zero factor property. I'll shorten it to prop, the zero factor prop. The zero factor prop says that if I multiply two expressions together, so let's keep it really broad. Let's not even use x and y. Let's say we have one expression and we're going to use a capital A to represent it. Now, A could be representing a number, or A could be representing an entirely other mathematical mathematical expression. It could be x minus 4 is what this A is. But if we take one mathematical expression and multiply it to another mathematical expression, capital B, which could also be anything, but if we multiply them together and we get 0, if you multiply two things together and get 0, there's no trickery here. What does that say about the things you multiplied together? Well, the only way you're going to get 0 out of multiplication is if at least one of them was 0 itself. So if A times B equals 0, then A equals 0 or B equals 0. One of the two is 0, or perhaps even both of them are 0. You multiply 0 times 0, you still get 0. That's what the zero factor property is. And you'll notice that it's not based on any higher level. We're just kind of reasoning here. We're just reasoning about the basics behind numbers. Well, it turns out then you can extend that. If you had A, B, C, D, you had A times B times C times D equals 0. If you had 4 different factors in there, that's okay. If they all multiply out and come out to 0, then at least one of them must have been equal to 0 in the first place. Otherwise, it's not going to work. That's actually pretty telling. And that's also the justification behind why whenever we solve like a quadratic equation, we want everything on the same side and then a 0 on the other side. But you'll see why in a moment. So let's talk about that. Let's say you have this expression, 3 times x minus 4 in parentheses times 3x plus 5, and that's supposed to equal to 0. And you're given the very broad task, solve that. Well, okay, most of you are just chomping at the bit because you know, oh, I set each of those factors equal to 0, and I solve each of the factors themselves. That's right. But the reason we do it is because of the zero factor property. We're going to solve each factor because whatever makes x minus 4, just this part, equal to 0. Whatever just makes this equal to 0, well, I'd plug it in, you can see it's a 4. I plug it in, this factor goes to 0. Doesn't matter what this one's doing. It doesn't matter what this one's doing. The whole thing wipes out and goes to 0. Whatever x value makes just this individual piece go to 0, I plug it in here, do a little math, and it comes out to 0. It doesn't matter what this guy was doing. The whole thing goes to 0. That's the justification behind why we set each factor equal to 0. And it wouldn't work if this was like a 5 over here on the right-hand side. It only works if this right-hand side is equal to 0. That's the whole point, and that's why when we solve things, we put a 0 on the right and everything else on the left. So we take each of these factors, set them equal to 0. Now, technically, the 3 here, that is a factor. But if you set 3 equal to 0, it's not going to work. You're not going to get anything out of that because 3 equals 0 is just nonsense. It's false. So we don't have to set the 3 equal to 0 because we can immediately tell it's not going to work. But let's do the x minus 4 equal to 0, and separately, let's do the 3x plus 5 equals 0. Over here, x minus 4 equals 0. Okay, add 4 to both sides. You get x equals 4. Over here, 3x plus 5 equals 0. Challenge accepted. Subtract 5. And then divide both sides by 3. So you'll get 3x equals negative 5. Divide by 3, and you'll get x equals negative 5/3. So we've actually just done it. We've solved this original equation here. The solution, 4 is a solution, but so is negative 5/3. Either one of them is perfectly valid as a solution. They both have their place. Now, if you were solving like an application problem and x was, okay, this is the length of this side of a square. Well, you would naturally throw out the negative 5/3 in that case because it doesn't make sense. Negative length is just, we're not thinking about it. So we just think about the 4 in that case. But at any rate, the solution set is negative 5/3, comma 4. Both of those are solutions to it. Now, some of you are thinking, maybe you've seen that before. Maybe you're saying, Josh, I already know how to do that. That's okay, but just keep in mind that we already started off with this thing being in what we call factored form. This is the easiest form. But imagine if we were to FOIL that out, distribute this 3, combine like terms, we'd have a quadratic because this x times this x will become x squared. So in the wild, you're not really going to get it in lovely factored form for you already. You're going to have to deal with, not factored form, and you're going to have to be the one to put it into factored form. So before we move on, do you guys have any questions on that? Any questions about how that works? Let me know. Give me a second to prime up to my next topic here. So we'll go over, since I don't see anyone in the text box, we'll go over exactly what, how we're going to factor. So let's see. Let's start with something like this. Let's say you have that quadratic equation. X squared minus 5x plus 6. Now, by a big group, yes or no, have you guys dealt with factoring something that looks like that before? Yes. Okay, just the yeses say yes. And the no's say no. Okay, so that's telling. So you guys have dealt with factoring something like that. I'll briefly touch on it because, again, factoring is not that interesting. Not that it isn't cool. It is cool. It's like slick, and you're like, ooh, I feel like a math magician or something. And that's a real thing. I had it whenever I was a kid at one of my birthday parties. I had a math magician. All the kids were crying. They were saying, why do we have a math magician? We just want to play video games. But, that was my parents. So x squared minus 5x plus 6. We remember, okay, since there's a 1 in front of the x squared term right here, then it's 1 times 6, which is 6. We're looking for two numbers that multiply to 6, but when I add those exact same two numbers, they come out to negative 5, and negative numbers are totally allowed, and it turns out those are going to be it. And so that's going to be negative 2 and negative 3. Negative 2 times negative 3 is the positive 6 required. But if I add those together, remember I'm adding negatives so they get even more negative. I get that negative 5 in the middle. So since you guys have expressed, you already understand that, that means that this would factor like that. And if you were setting equal to 0.
We need juniors, last name starting H through K, to the cafeteria.
That means once it's factored, now that it's factored, you apply that zero factor property. And you probably already knew that before. If you knew how to factor, you knew that you had to set each factor to 0. But I wanted you to see why we do that. It's not an arbitrary exercise. And so these would be the solutions to that quadratic equation. That's how you solve them. But okay, you're out in the wild, you're really not going to get to see factoring a lot. Now, to be honest, factoring to solve an equation is a little bit silly, like I said. There are other times where factoring is really helpful, though, especially later on in the semester. So I don't want to completely make fun of factoring and say, haha, factoring is pointless, because it's not. But it's just you have to realize that its scope is a little bit on the limited side. Now, the next thing we're going to do is we're going to talk about completing the square. Now, completing the square, that's where things get really interesting. Factoring doesn't always work. If I gave you something nasty, let's see, where's my drawing board? If I gave you something nasty, boy, 4x squared minus 123x plus 17. I gotta do 4 times 17 and try to, it's actually not gonna work. It's not gonna factor with nice integers, nice whole numbers. Now, theoretically, it can be factored, but we're not gonna overthink ourselves here. You're not gonna wanna solve something like that using factoring because it literally just may not work. Instead, you're going to need to use something called the completing the square. Completing the square. In your notes, if you're taking notes, if you're watching this video later, I would very much point you to, well, actually, you know what? I'll just do it myself. Give me 1 second. I would point you to the textbook, and on page 115 of your book, there's a nice little system here that shows you how to complete the square. I'm going to see if I can't put it on the whiteboard here. And it does not want me to paste an image. Okay, that's all right. Let me see if I can just share my paint. So boom, bada bing, bada boom. You guys can see that. Solving quadratics by completing the square. Dun dun. So these are the steps. I'll talk about them briefly. But unfortunately, just looking at a bunch of steps it's not like you're, suddenly I know how to do it. Maybe you've dealt with completing the square before, which is good. But these are the steps to it. In the ideal situation, your quadratic, you're going to have a 1 in front of the x squared. But you're not always going to get that. So sometimes you just have to live with what you got. When a is 1, you can skip step 1. If a is not 1, if you have something else in front of x squared, then life becomes a little bit more of a pain. So you're going to want to follow these steps. Square half the coefficient of x, factor the resulting trinomial as a perfect square, use a square root property to complete the solution. So maybe you have seen that before, maybe you have not. But let's go through it together. Let's work an actual completing the square problem. So let's try x squared minus 4x minus 14 equals 0. So x squared minus 4x minus 14 equals 0. Now for completing the square, if you're factoring, then that thing's already set up for you to factor if it could be factored. You have everything on the left-hand side written in nice, clean, descending order, and a 0 on the right-hand side. But we're not actually going to be factoring here. So for completing the square, if you look from those steps, excuse me, you will perhaps recall we actually want to get the constant by itself on the right-hand side. So that breaks our intuition a little bit. And I'm sorry, that's not 14x in the middle with Malcolm. That's just 4x equals 14. Now here's this silly little trick we're going to do. What we're going to do is we're going to introduce a new player into the field. We are going to take this 4x in the middle here. We're going to look at its coefficient, negative 4.
Junior, last name starting L through O. Please come to the cafeteria.
we're going to take that negative 4 and we're going to divide it by 2. So someone in the next pot, excuse me, I don't know what I was talking about. So negative 4 divided by 2 is going to become negative 2. So I'll write this off to the side. Negative 4 and little blue ink over here divided by 2 is negative 2. And if you remember from those steps I put for completing the square, we're going to start by dividing it by 2. Then we're going to take the product of that, or the quotient I should say, and we're going to square it, and that's going to give you 4. And so just only by coincidence was 4 the same as that, almost the same as that negative 4 over there. That's just a coincidence. And here's what we're going to do. It's funky, but we are going to take that 4 we just found through this process. We're going to add it to both sides of the equation. We are going to do that. So we need to add a 4 to both sides of the equation as I stall so I can clear that out. There we go. So let's do it. I'm going to add 4 over here. I'm going to add 4 over here. And now what I'm going to be left with is on the left-hand side, x squared minus 4x plus 4. On the right side, 14 plus 4 is 18. And I'm allowed to do that because I added 4 to both sides of the equation. Now, why did I add 4? Well, something magical is about to happen. If I could add any number I want to both sides of an equation at any time and equality is maintained, I haven't broken any rules. But I don't want to just add a 67 to both sides of the equation. I specifically chose 4 because something magical is going to happen here on the left-hand side. If you factor the left-hand side, and I know I just spent a few minutes making fun of factoring, but it's still semi-helpful. If you factor the left-hand side, well, it turns out by taking half the coefficient here and squaring it and then adding it to both sides, we introduce something that can be easily factored. In fact, it factors as something we call a perfect square trinomial. So just looking at the left-hand side, we're ignoring the 18 at the moment. Let's see, what are 2 numbers that multiply to give me this positive 4 here, but when I add them, I get negative 4? Well, you probably see that those 2 numbers are negative 2 and negative 2. The same number twice. In fact, we chose this thing that we added, the 4 over here that we added to both sides. We chose it so that we would have a repeated factor over here on the left-hand side. That factors as x minus 2 times x minus 2. But wait a minute, I have the same factor twice on the left-hand side. If I multiply something to itself, I'm really just squaring it. So now I get to come over here and simplify that to x minus 2 squared equals 18. And now you see the gears turning. The whole reason we were all the way back here and said take half of this thing and square it is so that we'd get this perfect squared trinomial situation. Remember earlier we factored x squared minus 5x plus 6, and that came out to x minus 2 times x minus 3. That was not a repeated factor situation. Those were 2 separate factors. But this thing was engineered, it was designed according to those steps to create this situation where it's just this squared. And now a little bit of mathemagic is going to happen. We would apply the square root property. So apply the square root property. Oh, okay, magenta, that's cool. That's going to get rid of the square and the square root on the left-hand side. Remember, we need to introduce mentally, and we have to remember to introduce a plus or minus on the right-hand side. So what we're left with is x minus 2 equals plus or minus the square root of 18. Oh, now you see why we did all this. Now you see the gears turning. We just need to add 2 to both sides now, kind of like we did with the previous problem. And now we get x equals positive 2 plus or minus the square root of 18. Ooh, everyone say ooh. I'll assume you said it. I don't think you did, but that's okay. Next time we'll be in the ooh mood. The mood. So yeah, we get 2 plus or minus the square root of 18. And now we've actually just solved it. They're not nice, pretty solutions like 3 and 7. It's a little bit ugly. 2 plus the square root of 18 is not going to come out to be a pretty number if you put it in your calculator. But very, very rarely do we get to have nice, pretty solutions to things. But at least we had a nice, straightforward process to finding those solutions. And so now the final answer is x equals, you can either do 2 plus the square root of 18, also 2 minus the square root of 18. And then you might remember, this is totally on the side here, you don't have to know this per se, that square root of 18 could be written as 3 square roots of 2. But you'd have to remember, make your prime factorization tree. That's something we might go over. So then it could be written as 2 plus or minus the 3 square roots of 2. Now, the ugly.
All juniors, last name starting P through S. Please report to the cafeteria.
Now, the ugly truth behind everything is if you don't have a 1 in front of your x squared term. We did in this case, and everything went just nice and dandy. If you don't have that case, you're almost certainly going to be dealing with fractions. So what I think we should do, we'll ask for permissions, or we'll ask for forgiveness instead of permission. Let's jump forward and let's talk about what is the end all be all of completing the square. Completing the square is wonderful. It's exactly intuitive to what's going on in the process. And you saw everything when we completed the square. We didn't use any new magical tricks. All we did was kind of play around with math a little bit. Well, now we talk about quadratic equations, and now what we can talk about more importantly is solving them with the quadratic formula. Quadratic formula. And I'm putting all this pop and circumstance on it because the quadratic formula is just the bee's knees, let me tell you, ladies and gentlemen. The quadratic formula is what we call a black box formula. It always works. It doesn't matter what you start with, it is always going to get you to the solution. Completing the square also does that. In fact, it turns out this quadratic formula that I'm about to share with you guys it was derived by completing the square for general coefficients A, B, and C. What do I mean? Well, let's say your goal is to solve this standard quadratic equation, ax squared plus bx plus c equals 0. What we want is a formula that, as long as we know what the coefficients are, as long as we have an a b, and a c, we can solve this equation. We can solve it in general. It turns out the solutions, and I'm sure you've seen the quadratic formula before, maybe not. It turns out the solutions can be found using this formula. Now, everybody who studied math very seriously, especially if you studied it at high levels in college, if you've paid close attention during your math, every mathematician has the quadratic formula written on their brain. Negative b plus or minus the square root of, and it looks a little bit nasty. That's an A, C all over 2A. It looks like something you'd see like in a math movie or something about a bunch of people writing stuff on a chalkboard that looks mathy, and the writers of the movie just were like, yeah, just throw a bunch of random symbols together. That's math. It's kind of what it looks like. Quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a, where a, b, and c just come from the standard quadratic formula over here. Well, let's investigate that. Negative b plus or minus the square root of b squared minus 4ac all over 2a. It turns out this was derived using completing the square and just leaving them as a, b, and c when you did it, instead of having actual numbers for them. And you can kind of see the blueprint of that. There's the plus or minus thing. There's the square root here. There's something inside of it. you can kind of see what happened. There's even, you're dividing the whole thing by a here, which remember, we might have to do that if we had like a 3 or a 4. We would have had to divide both sides. So that's kind of, we see what's going on here. We see the gears turning. Why is there a 2? Well, it turns out that's just how it ends up being derived. So I'm going to introduce the wonderful magical, it's not magical, quadratic formula for all of you today. And next class is when we are actually going to be dealing with. So for the last couple minutes here, I just want to remind you of a few things. I'm going to quit sharing the whiteboard. Stop moving, sorry. It gets in my way. There we go. So for the end of class here, and I'm going to go